Cylindrical fuse operation time. Fuse consists of a glass tube filled with a quartz sand. There is a thin conducting wire in the tube. The wire is soldered to the end cups with the link contacts. Fuse rated current is 5 amperes, and our task is to calculate the operation time at the fault current of 20 amperes. This problem is essentially multiphysics. First, we should simulate DC conduction problem to calculate current density and the Joule heat distribution. Then we should pass Joule heat distribution to transient heat transfer problem to calculate temperature rise dynamics. And initial temperature is 20 degrees Celsius. Let's run QuickField and create new problem. Problem name is fuse. Next. Problem type is DC conduction. Geometry of the cylindrical fuse features axial symmetry, so the model class is axisymmetric. Length units are millimeters. Finish. On the left you can see the problem pane, and on the right you can see the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD DXF file. I have the geometry model already prepared. Here is the file, and I will open it. In QuickField, the axis of the rotation is a horizontal one, and we should place the model symmetric to the axis and then remove all parts located beneath the axis. So here you can see the cross section of the fuse, only half of the cross section. There are several geometric objects here, and to distinguish one geometric object from another we should assign labels. Through labels we also specify physical properties. Switch to the selection mode and click and select the block. Follow to the properties dialog and type in the label name. This is the sound. OK. You can also use the rubber band to select multiple objects. For example, these and these objects are conductors made of copper. OK. Let's zoom in. Switch off the zoom in mode, and I select this object. This is the glass tube. Glass. And this thin wire is the fuse. Again, I will zoom in, switch off the zoom in mode, click the object, follow to the properties, fuse. OK. Now you can see all new labels in the tree with the question mark next to the name. We should specify physical properties to these labels. Double click the label sand. For the sand we do not specify electric conductivity, just open the dialog and click OK. Now you see instead of the question mark we have the exclamation mark. This mark indicates that this is not an unknown label. This is the label with empty data set, and this label is excluded from the simulation analysis intentionally. The same for the glass. For the copper I specify electric conductivity, which is 55 megasiemens per meter. Okay. And for the fuse I specify electric conductivity, which is 5 megasiemens per meter. Okay. That is all for materials. Next, let's deal with boundary conditions. We should define current source and the current sink. Let the sink be on the right and have zero electric potential. I select the edge and assign the label 0. Okay. And for this label I specify zero electric potential. Okay. Then the current source is on the left side. I select the edge, open properties and type in the label I+. Okay. For this label I should specify normal current density, which is current divided by the cross-section area. Well, the current is 20 amperes and the cross-section area, let me check. This is a cylindrical conductor and conductor radius is 0.5 millimeters. Then for the current I can type in 20 divided by the P multiplied by the radius, which is 0.5 millimeters. 0.5 millimeters converted to meters squared. Current divided by the cross-section area. Okay. That is all for the geometry model and the labels. The last step is to build the finite element mesh. Just click this button and the mesh is ready, and we can run the analysis now. Yes, save all simulation files. Now we can take a look at the result. Here you can see the color map of the current density. You can adjust the field picture. You can switch on the color map of electric potential, and I would like to make sure we have defined the current source correctly. I will use the contour tool to calculate total current passing through the fuse. Draw the contour line here, follow to the integrals, current for the surface, 20 amperes, as it should be. And here we can calculate the fuse resistance, which is 0.83 volts divided by the current, which yields to be 41 milliohms. What else? Let's zoom in and I will adjust the field pictures. Switch on the vectors of the current density. You see small vectors, low current density, large vectors, high current density. I can also switch the color map of power loss. That is power loss density, watts per meter cubed. It is hard to interpret these values, so I'd better use again the contour tool, contour clear, add to contour. This time I will click inside the fuse and now I can calculate the total joule heat in volume, which is 16 watts. Well, this is a bit too much for a small fuse, Probably the wire temperature should be high. Let's find out. I create new thermal problem. Fuse heat. Next. Problem type is transient heat transfer, as I would like to get fuse heating dynamics. Model class is again axisymmetric. Length units are millimeters. I would like to pass Joule heat distribution from electric problem to heat transfer problem automatically. And to be able to pass data from one problem to another, both problems should be based on the same geometry model. So I click in the geometry model file name field and then click Browse button. And here I should find fuse.mod file. Here it is. Open. Next. For transient problems, we should specify final integration time and time steps. I choose the final time to be 60 seconds, and I will let QuickField to adjust time steps automatically. Initial temperature is 20 degrees Celsius. Finish. So the geometry model is the same and we have already assigned labels, but now we should define thermal properties to these labels. For copper I specify thermal conductivity, which is 380, specific heat again 380, and density 7,800 kilograms per meter cubed. For the fuse, thermal conductivity is 60 watt per Kelvin meter, specific heat is 320, and density 7,400 kilograms per meter cubed. You see, I have not specified the heat source here. I will import heat sources from electrical problem, so I leave 0 here. Okay. For the glass, thermal conductivity is 0.8, specific heat 840, and the density 2,500. Okay. For the sand, thermal conductivity is 0.3, specific heat 2000, density 1,500. Okay. We have finished with material properties. Now what about boundaries? The fuse is located in the air and cooled by the air, so I should select the side surface, hold the Ctrl button pressed to select multiple objects at the same time. And for this surface I will assign the label cooling. Now for this label I specified the convection coefficient, which is 5, and the ambient air temperature, which is 20. Also for the heated bodies we can specify the radiation coefficient, which I believe should be about 0.7, and the same ambient air temperature. Okay. The contacts are connected to some external wires which are not included in our model, and I will specify 0 heat thermal flux there. Now let's set up the link. Open the thermal problem properties dialog and follow to the links tab. Here choose the imported data type, generated heat. Browse for the problem file, which is fuse.pbm. Browse fuse.pbm. Then click the Add button. Now the link should appear in the tree. Here it is. And we can start the analysis now. Oops, we got the error message. The linked problems results are out of date. What does this mean? Remember, we have assigned new label to the fuse boundary. So we have modified the geometry model. We have specified these label properties in the thermal problem, but electric problem doesn't know about this label. Open the label properties. In fact, this label has no physical meaning in electrical problem, so I do not enter any values here. Just click OK, and you see this label is marked with 0, which means this label has no data assigned and should not affect the results. Anyway, the problem setup has changed and we should run the simulation process again. Solve, yes, save model file and save data file. Yes, we can see the results now. Let's check again the current value. The same 20 amperes. Now we can proceed with the thermal analysis. This is thermal problem. Solve, yes, save all simulation files. This time there is no error message and the simulation process has started. Now thermal problem has been solved in about 7 minutes. Let's take a look at the results. You can see the temperature distribution at the final moment of time, which is 60 seconds. In transient problem you can select the time layer. To adjust the scale, just double click it. So the maximum temperature at this moment of time is about 600 degrees Celsius. You could get more accurate data if you use the local values. Just click the point and here you will get the temperature. Remember, the melting point of the fuse is only 240 degrees Celsius. So at which moment of time the fuse has melted? It's easy to find out. Right click and choose the time plot. And here you will see that the fuse would melt about 0.5 seconds after the fault. That is the fuse operation time at 20 amperes fault current. What would be the operation time if the fault current is 15 amperes? That's easy. Change the current load in the electric problem. 15. Run the analysis again. Electric problem has been solved. Now let's make sure that the current value is indeed 15 amperes. Correct. Now we can run thermal analysis. Thermal problem has been solved. Let's take a look at the results. Again, I will use the picker tool. Click the point and take a look at the time plot. When the fault current is 15 amperes, the operation time is 1.6 seconds. At 20 amperes, operation time 0.45 seconds. At 15 amperes, the operation time is 1.6 seconds. This way you can find out fuse operation time versus current dependency. At our website you can find the page related to this example. There you can read about problem setup, find the picture with the results, and download the simulation files.